In this video, I want to investigate the types of applications of higher order differential equations. And in this case, we're going to be focusing exclusively on initial value problems. We will look at boundary value problems in a separate video. The main model that is going to be relevant for these higher order differential equations is going to be a mass spring system. And so this is literally a mass attached to basically a spring and hanging from some fixed surface, if you want to think about it that way. So basically, let's start with a mass spring system. And talk about what this actually looks like. So imagine that we've got basically a ceiling here of some sort. And hanging from that ceiling is some spring. And this is the normal length of the spring. So right now it's unstretched. Maybe this distance here is some distance that we could call L. And we're going to attach a mass to this spring. So let me take another look at another spring here. So same spring. And when we attach a mass to it, that mass will stretch the spring. And so now the length that used to be, if I can kind of do a dotted line here to indicate the old length, here's the old distance L. And we've stretched by an additional amount here that we can call S for the amount that it's stretched. And so now, if we were to basically let the mass come down to this height and kind of hold it there and let go, it would be hanging at this equilibrium position where we have the force of gravity pulling down on the mass, but we have the force of the spring kind of pulling up on the mass so that the mass is not moving. The idea here is that there are basically two competing forces. So first is the force of the spring. So the spring, which is forced upward, this comes from Hooke's law, which is basically the physics law that dictates how springs work, essentially. So how the force of a spring works. And Hooke's law says that the force of a spring, which I'll denote with a little subscript of S, is basically equal to something where it's proportional to the amount of stretch in that spring. So how much you've stretched that spring. So this is called a spring constant, the value K here, and S is a distance. So it's a length of, in this case, stretch. Later on, we will use the variable x when we start talking about this length scale that we're going to be using. But for now, it's basically how far you've stretched the spring. And so basically it says that the force of a spring is going to be proportional, that's what the spring constant is, to the distance or length that the spring is stretched. The farther you stretch the spring, the stronger the force will be. And this works not only for stretching it out, but also for compression on a spring. If we were to start to compress the spring, the more you compress it, the greater the force, sort of the restoring force, trying to put that spring back to its sort of equilibrium position. So the first competing force is the spring, and the second competing force, we said, is basically the force due to gravity. And so the gravitational, basically, so gravitational force is given by, if we look at the force of what we'll call gravity here, it's equal to a mass times the gravitational acceleration constant on Earth's surface. So it's equal to m times g. So this is the idea. Both of these have units of force. So both forces have the same units. And again, this isn't a physics class, but the units of force are newtons. But if we want to write them out, it's basically a mass times let's do it this way. It's going to be a mass times an acceleration. I don't know why I wrote that offset there. So I have units of mass times acceleration. And so depending on which units we decide to use, whether we're going to use kilograms or whether we're going to use slugs, which is the mass unit in imperial units, and whether we're using for acceleration meters per second squared or feet per second squared, all of that doesn't matter. We'll do examples using both types of units, but the point is both of these have these same units of force. So we can figure out in this case what the units of each of these two terms are. Right? In this case, m is the mass, and g is the gravitational acceleration. So that one's easy to see what those units are. Up here, this one's a little bit harder to see. We just said if s is a length scale, then that means the spring constant has to have some kind of weird units. So if s is a length, and we try to think about how we measure acceleration. Usually acceleration can be thought of as maybe meters per second squared, so like a length over a time squared. That would be the easiest way to write it. So this is length over time squared, and mass is obviously just going to be mass itself. So over here, we've just taken care of basically the length scale. So we have a length that the spring has been stretched, so that means k has to have the remaining unit. It has to be mass over time squared. And so that's what the units of the spring constant are. They're going to be mass over time squared. Okay, so here's the idea. We've got these two competing forces, and when they're totally in balance, when they balance each other out, then the mass itself will be hanging in equilibrium. So when the forces balance, meaning when Ks, or let me just write it in terms of the Fs, when Fs is equal to Fg, because one is pointing, in this case, gravity is going to be pointing downward, and the spring force will be pointing upward, right? So we basically have these two forces, one pulling up, one pulling down. Oops. Let me draw them so that they're vaguely the same length here. We have one pulling up, one pulling down. Here's the force due to gravity pulling down. Here's the force due to the spring pulling up. When they're equal to each other, the mass is at equilibrium. And all that means is it's literally not moving. The forces are in balance, so it's done moving. This sets up a differential equation. So I just want to, again, do a quick overview of the physics here. The physics say that when you have these two forces being balanced against each other, our mass will be at equilibrium. The two forces are the force of the spring, which is determined by Hooke's law, given here, and the force due to gravity, which is given here. When these two are at balance, the object is not going to be moving. And so this is really, really a nice way that we can set up the problem. We can then start with Newton's second law and a force balance to come up with a differential equation. So now, using Newton's second law, which is F equals ma, exactly what I basically described over here, that force is equal to a mass times acceleration. That's Newton's second law. We can set up a force balance. A force balance equation. Okay. So what that force balance equation is going to say is essentially the following. Imagine that we want to take the mass that we had up here and we want to stretch it even further and then let go of it. What would happen if we were to take this mass, stretch it down, and let go? Well, at that point, we will have pulled the spring, stretched it out even longer. And by stretching the spring here, what will happen is that this force here of the spring force will outweigh the force due to gravity. And so the force pulling upward will be stronger than the force pulling downward. And what would happen? Sort of the obvious thing, when you pull on a mass that's going to be hanging here, it's going to kind of shoot back up. And it'll come back up, and then it'll come back down, and then it'll go back up, and it'll go back down. It'll start oscillating back and forth. This is the motion that I want to capture in a differential equation. Okay, so if we pull the mass a distance of whatever we want to call it, let's say x, past the equilibrium point, and let it go, it will basically shoot back up and then begin to oscillate. Oscillate. Okay. So basically, here's our mass again, hanging from the spring. Let's say that this distance here is the equilibrium position. If we go back up to the picture here, so this position here, this is what we'll call equilibrium. So that equilibrium position is the combination of the natural length of the spring, L, plus the distance S that the mass normally would stretch that spring, L. Past L, I should say. So this new distance, the equilibrium distance here, is L plus S. It's the combined distance of the L, the natural length of the spring, plus any distance that the mass stretches that spring. So that's our equilibrium position here. And at this equilibrium position, I want to say, here, so here's the normal mass. I want to take the same thing and extend it now further than that. So I want to pull this mass down beyond that point. There's our mass again. Here is the old equilibrium position. Right, there's the L plus S. And here's some additional distance that we've stretched it, a distance x. And we're letting it go, and it's going to shoot back up, and then it'll come back down, and then go back up and back down and oscillate back and forth indefinitely. So that is kind of the picture that we're looking at. If we keep track of these forces, obviously this mass, our intuition tells us it's going to go back up. Once it goes up high enough, gravity will take over and it'll come back down. In fact, it'll start to compress the spring at a certain point, and so the force of that compression will start having the spring be wanting to push down on the mass. And so it'll come back down to here and then go back up and then back down and back up. And we want to keep track of basically how is the force changing over time, and how can we use that force changing over time to eventually figure out what the motion is of this mass as it oscillates back and forth. So basically, the total force is going to be equal to the force of the spring plus the force of gravity. And we just need to keep in mind that at least here at the equilibrium point, those two forces point in opposite directions. So what we're going to have to do is assign a negative sign to one of these. And to do that, what we'll do is decide which direction we want to consider positive. So we basically need to assign an axis here, and oftentimes this will be the positive x-axis, so to speak. So down will be the positive direction in what we're going to write here. So that total force, which is a mass times acceleration, will look like this. We have a mass, m, and the acceleration is given by the second derivative of the position of this of the mass that we're trying to keep track of. And it's going to be balanced by basically a couple of different forces here. So if we think about it at rest, so let's do this at equilibrium and see what we get. So at equilibrium, we know that these two forces are basically the same. So let's see if I can get this whole thing on the picture all at once. Okay, so again, we have the force of gravity pulling down, we have the restoring force of the spring pointing up, and these are the values of those two things. And so what we can do is basically say that at equilibrium, we have the force of the spring, which I'm going to write as negative Ks, and we have the force of gravity, mg. And I've assigned the negative sign to the spring force because the spring force is what's pulling upwards. So remember, the spring force is up, gravity is down. So because we decided that this is our positive x direction, downward is the positive direction, gravity gets a positive sign, and the spring force, which points upward, has the corresponding negative sign. But at equilibrium, what do we know is happening to this spring? What is the happening over here with this acceleration term, right? We have the d squared x dt squared. Well, at equilibrium, this is 0. And so these two forces are balanced. Hopefully that makes sense, right? So at equilibrium, the two forces are in balance, the object isn't moving, which means this acceleration goes to 0. But now let's say we're going to consider the case, like we said here, where we stretch the spring past the equilibrium case. So here's our equilibrium case over here. And over here, let's do the not at equilibrium case, which we said will eventually yield some actual motion. So the acceleration isn't going to be 0 because we're going to see this thing oscillating up and down. So we're going to have some motion, and this term will not go to 0. So when we're not at equilibrium, when we've instead pulled that mass an extra distance x away from here, which means that this equilibrium point, it would be really nice if we kind of considered this on our so-called x-axis here. Let's consider this to be the origin in terms of that x-axis, so that our x-coordinate is just the amount, or we can think of the position of the mass, which is going to be oscillating around this center line of 0, as being either positive when it's stretched down below it, or it would be a negative position if it oscillates back up above this equilibrium position. Okay, so when it's not at equilibrium, what's going to happen? Well, in this case, let's get the whole thing on the screen here at once. On the left-hand side, we're going to have the same thing. So here's our term that shows sort of our net total force. And it's going to be equal to, again, two separate pieces, the restoring force of the spring and gravity. The force of gravity isn't changing, the mass hasn't changed, so that term's not going to be any different. This one will stay the same. But this one is going to be different because now, instead of having stretched the spring just a distance s relative to its natural length, right? at equilibrium, we've just stretched it a distance s. Now we've stretched it a distance, an additional distance of x past that s point. So here's the old natural length of the spring. If you want to think about that, that would be over here. Draw them all together. That means that that total distance is the L plus S, but this little distance is the S. And so what is the distance that we've now stretched the spring past its natural length, which is L? Well, the weight of the mass stretched it a distance S, and then we manually pulled it down an additional distance X. So it's the combined distance S plus X. And so in this case, we get negative K times the total distance that we've stretched the spring, which is both the S plus X. So S is the distance that the mass stretched the spring, and X is the additional distance that we've now pulled it past that equilibrium point. But as I said before, the gravitational force hasn't changed. So we get this for our equation. And if we distribute through, we will get, so let me not touch the left-hand side yet, but on the right-hand side, I'll get negative Ks minus Kx plus mg. But can we simplify this equation? And the answer is yes, because I know that the negative Ks plus the mg term, that those two pieces together have to add up to 0, according to the equilibrium equation. This force is exactly the force that counterbalances this force. This is the new additional force that we've gotten by stretching the spring an additional distance x. So these two terms right here wind up canceling. And our equation just becomes m d squared x dt squared equals negative kx. So this is the equation that we're looking at right now. If we moved everything over to one side of the equal sign, a common way that you'll see this rewritten is basically m d squared x dt squared plus kx equals 0. And so this is basically our differential equation. This is our ODE for the free motion of this mass spring system. And I'm going to put a word here that we'll define in a minute, but it's for an undamped mass spring system. So it turns out there's an additional force that we could add in to our model. And it's common on places where springs tend to show up in real life. So for example, if you've ever looked at the suspension on a car or a bicycle, they will often have both a spring that is used to help with the suspension, but also essentially a damped piston. So oftentimes the shock absorber in a car looks something like this. It's basically has some sort of strut that has essentially walls with some piston in it and some fluid, and this piston acts as a damper. You can compress the fluid, but it doesn't compress very much. And then on top of that, you'll have a spring that essentially kind of surrounds it that wants to push this way to restore the shock absorber back to its full length, its equilibrium length. So this is the idea. We can add in addition to the spring, we can add a damper, and that will give us another term in this system. But for now, this is what we call an undamped mass spring system. So let me turn to a more general version. If we add in damping, which essentially you can think of as a friction force. So if we add in damping, so you could basically think about putting this mass that we're dealing with into that piston with some sort of fluid compressing on it, or even just literally suspending it in a fluid that applies friction to it where the viscosity of the liquid itself is enough to slow the spring as it oscillates. But if we add in damping, we get the following big full mass spring system. And this is the model that I want to focus on primarily. So this mass spring system model, it'll have the terms that we wrote before. So we'll have m times d squared x dt squared. Then we will have that damping term. And I'm going to use the letter beta for the damping coefficient. And it's proportional to the velocity. The friction increases as the velocity increases. And lastly, we have that restoring force of the spring, so we have our plus kx term. And it's possible to even add some other sort of external forcing term to the whole thing. So over here, you'll notice comparing these two models, the old one had two of the terms. It had this term and this term. And we've added in this one, which represents damping, which is always going to be, again, proportional to the velocity. dx dt is the velocity. So the faster something is moving, the more friction it will feel due to, wind resistance or fluid resistance or whatever medium the object, in this case our mass, is moving through. And it's also possible to apply some sort of external forces to the mass. Maybe there's an external force being applied using magnets or using something like that, which also can happen in a car suspension system. They have different ways of having basically the suspension of cars react and have a computer that senses things and applies a magnetic field. And oftentimes they'll either use a ferrofluid, which will change the damping, or an actual magnetic resistance to apply some external forcing to the whole system. So this is the whole picture of what we can have in a mass spring system. The units that we have here are, again, this is the mass, right? This is acceleration. This is our damping coefficient. This is the velocity. K, we said, was the spring constant. Constant. And K is basically the displacement or position. And this F of t term is what we'll think of as an external force. External forcing term. So here's what all the different pieces can look like. Okay, so for now, we're going to basically assume that the f of t is equal to 0, so that there is no external forcing. And when we do that, what we wind up with here is an equation that looks exactly like the ones that we were solving back in section 4.3. It'll be a homogeneous, second order, constant coefficient differential equation. The mass will remain constant, the damping coefficient will be constant, the spring constant will be, again, constant. So these will all be constants. We'll have a constant coefficient, second order, linear differential equation, and in this case it'll be homogeneous because the right-hand side will be 0. We will later add in these forcing terms to the right-hand side to get non-homogeneous systems or non-homogeneous equations as well that we will be able to solve using the methods from sections 4.4 and 4.6. So that's the idea, though. This is a second-order differential equation, and it models a mass spring system. And mass spring systems are nice because, again, it's something that we all kind of have some intuition for how we would expect something like this to work. Let me talk about the types of things that we can expect to see. So if we assume that that f of t is equal to 0, so no external forcing is being applied, then there are a few possible outcomes that we can get in terms of the motion that we can expect to see. So a few types of behavior to expect. Okay, So let's kind of draw our picture again here, where we've got our, let's imagine this is our fixed ceiling. Drawing these lines to make it hopefully look vaguely like something solid, substantial. And we have case number 1. We have the mass hanging down here, and it's not moving at all, right? So let's draw our x-axis here. This is our x-axis, and again we said that right now I'm going to call this position 0, essentially. So in this case, if we leave the mass at no initial displacement, it's hanging at the equilibrium, right? This is right here, our equilibrium position. This was the point where the force, the restoring force of the spring pulling up exactly matches the force of gravity pulling down. If I start with the mass hanging at this position and I give it no initial displacement and no initial velocity, what will happen? Well, in that case, if I don't do anything to this spring, nothing's going to happen to it. It's not going to move. If it starts at equilibrium and I don't displace it beyond equilibrium and I don't give it any initial velocity, it'll just sit here indefinitely. So in this case, it's going to sit forever, no motion, so no initial displacement, and that means no movement. But what are some other things that could happen? What if instead we start with the mass spring displaced by some amount? So here it is hanging, and we've basically pushed it up a small amount. Right, so here's the equilibrium point. Clearly there's some displacement. And let's assume that there is no damping in this case. What will happen? If there's no damping, what we'll see is that the mass will start off by moving downward, then it'll come back up to the original height, then come back down, then back up, and it'll continue to oscillate like this forever. So this is what it would look like. There is initial displacement. And there is no damping. This is the type of motion that we would expect to see. Let me carry my little dotted line over here. What if we do the same thing? So same starting situation. So right, here's our displaced mass, same initial displacement, but now we have some damping. What would happen if there's some damping, some friction? Well, what we'd see is we would expect it to start to oscillate, but because of the friction, it wouldn't quite return to its full height when it oscillated back. And then when it oscillated the next time, it would get even less and less and less. And what we'd see is basically, hopefully you can kind of see this, the heights of the oscillations are decreasing over time. So this is sort of what we would expect to see. Again, given some initial displacement, but now there's some damping. Not necessarily strong damping, but some. If the damping gets strong enough, so we have really strong damping, what would that look like? Well, it's possible in the case where we have really strong damping that the mass can either go past just once and then level out, or if it's really strong, it may not even ever oscillate past that center line. So we may get it to only go like this and level off. So same thing, initial displacement, but very strong damping. Right? Basically, if we make it so that the damping term, the friction term, is so strong that it totally outweighs the force due to, for example, the spring, it won't let this thing actually oscillate. it may just do a little smooth return to the equilibrium position that looks like what I just drew there, or alternatively, maybe goes past once and then returns to that, but never actually oscillates. So these are the different types of things that we might see. This term where we see some damping, this is often referred to as an underdamped system. So we see some damping, but we still see oscillations. So this is often referred to as what we call underdamped. And this other case where we don't see any oscillations, this is what we refer to as overdamped. And right in between these two cases, there's often something that we refer to as critically damped. Basically, right when it transitions between these two cases, critically damped. And we'll look and see mathematically what those solutions look like as well. So if we don't do anything to it, it's not going to move. If there's no damping, but we displace it, it's going to oscillate forever at basically just the same amplitude indefinitely. Right? There's no friction. There's nothing to keep it or stop it or slow it from oscillating. So it'll just keep oscillating indefinitely. But if we add some friction, we'll still see those oscillations, but those oscillations will decrease in amplitude over time, getting weaker and weaker. And if we have really strong damping, we may not see any oscillations at all. It'll just go basically maybe past it once and then to the equilibrium point. So these are the different cases that we would kind of intuitively expect to see. I want to show that we're going to actually get these exact same behaviors mathematically when we do the math on all of this. Okay, so far this has been very, very physicsy. Let's make this a little bit mathier, and let's kind of look at what's going on in some of these situations. So instead of solving the differential equation in this form, where all of these coefficients are sitting out in front of their respective terms, oftentimes it's convenient to get the leading order coefficient to be a 1. So this second derivative term, if the coefficient here was a 1, in general, that's going to give us characteristic equations that are a lot easier to solve. And so that's usually the first step, is we're going to take this equation and we're going to divide through every single term by the mass and rename this. Okay, so how do we solve this? So solving these equations. Okay, so instead of solving the equation as I wrote it a minute ago, so m times d squared x dt squared plus beta times dx dt plus k times x equals our f of t, we'll divide by the mass. And when we divide by the mass, what we'll get is d squared x dt squared plus what I'm going to call 2 lambda times dx dt plus what I'm going to call omega squared. It looks like a little lowercase w. This is the Greek letter omega, and we are squaring it. Omega squared k equals some new function on the right that I'm going to call capital F of t, where the connection is that basically this thing that we're calling the 2 lambda is just the old beta divided by m. So the old damping coefficient divided by m. So our 2 lambda is just the old beta divided by the mass. And similarly, the omega squared is the old k divided by the mass. And our f of t is just the old f of t divided by the mass. The reason that I've included an extra 2 sitting here, and the reason that instead of calling this just some variable omega, I've instead called it omega squared, it will make our math easier down the line. So I've done this intentionally, and this is the notation that's often used because it'll make our algebra much cleaner. So there's no reason that you would know to do this until we actually go through the algebra and see what this leads to. But basically, we're going to be able to find some things in terms of lambda and omega as long as we include them with this extra coefficient of 2 and have the omega being squared right here. So one thing I want to keep in mind is we're absolutely allowed to do what we just did because the mass, by definition, has to be greater than 0. Right? So keep in mind that all of these terms up here, in fact, have to be greater than 0. The spring constant has to be a positive number. This damping coefficient, beta, has to be a positive number, and the mass has to be a positive number. So it is safe to assume that this k over m term, which is omega squared, obviously omega squared has to be positive because it's some number being squared, but k over m, k and m are both positive to begin with, so we can safely make that assumption, right? These are safe assumptions. Because m, obviously a mass has to be positive, but basically the beta and k, the spring constant and the friction coefficients, also have to be positive in order for them to work the way that we would expect. Essentially, if these terms were negative, if the damping term were negative, when something is moving with the velocity, the force would be giving it basically an extra boost in that same direction as opposed to opposing the force of the velocity. So that's how we know that this term has to have a positive one. If we went and kind of did our force balance and compared, it always is going to basically, the force will always wind up being set up in such a way that it opposes the current velocity. Friction force always opposes current velocity. And same thing, we already talked about the spring constant, which direction it needs to go. But all of these are all greater than or equal to 0. Okay. So again, why did we put a 2 here? Why are we calling this omega squared? It's because of the characteristic equation. This is convenient because our characteristic equation looking at this differential equation, the characteristic equation for the left-hand side is now going to be the following. Let's see here. Normally we used m before, but I've already got m being used for something here, so I need some other variable. I don't know, I guess we can call it r. I think we did maybe r at some point. Let me see what the book uses. I'm not sure what the book uses. Let me try to be consistent with what they use. Hold on just a moment and let me look that up. All right, so it looks like they use m, more or less. So I'll just have to make it very clear that the m that I'm using here is not the mass, right? We're dealing with this equation. The m that I'm using is not the mass. If you'd prefer to use a letter like r, that might make more sense because it doesn't conflict with any of the named variables that or parameters that we've already picked. So basically, the corresponding equation, characteristic equation for this will be m squared plus 2 lambda m plus omega squared equals 0, right? This is the characteristic equation for the homogeneous version of this differential equation. And our goal is to solve for m. So let me just say, if we were to use like r or something instead, it would be r squared plus 2 lambda r plus omega squared equals 0. Either way, our goal is to solve for these values here, r or m, and see what the solution, the form of the solution will ultimately take. So let's solve for this. We can just plug directly into the quadratic formula to find that from this equation, we're going to get m is equal to Remember, the quadratic formula says negative b, and in this case, our b is the coefficient of the middle term, so negative 2 lambda plus or minus the square root of b squared, so 2 lambda squared, minus 4ac, so minus 4 times the coefficient here is 1, the coefficient here is omega squared. So there's that term, all over 2a. Okay, so there is what the quadratic formula looks like. By design, making this have a coefficient of 2, I'm going to be able to cancel with this 2 down here. And it'll also be nice because I'm going to have a 4 in here and a 4 here that I can use to basically do some additional cancellation. So all of this looks a lot nicer when we actually write it all out. So I'm going to have negative 2 lambda plus or minus. This term inside of the square root is going to become a 4 lambda squared minus 4 omega squared, whole thing over 2. Again, we can factor the 4 out, the square root of the, and we can even pull it outside of the square root sign. It'll just be a 2 outside of there. So we've got negative 2 lambda plus or minus 2 times the square root of lambda squared minus omega squared over 2. Cancel these 2's. And we get that m is equal to negative lambda plus or minus the square root of lambda squared minus omega squared. And this is really nice because now both of these terms that I'm comparing in here are squared. That's why we introduced the square here. And similarly, the reason we introduced the 2 here was so we would get all this cancellation of all the 2's when everything worked out. And so this is basically the result that we wind up with for all of this. Notice again that because we knew that this coefficient beta was positive and the mass was positive, those were all assumptions we made, that means lambda itself also has to be positive. And that means that this term sitting right here is always going to be a negative term due to the minus sign sitting in front of it. That will be something that will be helpful to keep in mind going forward. Okay. This leads to 3 possible cases. Okay, so just like when we found the form of using the quadratic formula back when we were first looking at homogeneous second-order differential equations, we got 3 different cases. Those same 3 cases are going to exist here. So let's take a look at each of the possibilities. Case 1. So the first case, let's pick that this term inside of the square root is a positive term. So let's pick lambda squared minus omega squared to be greater than 0. That's our first case. This corresponds to what we call the overdamped case. And we'll see that in a minute. The solution is of the following. So the solution, what we were calling our x, or at least the homogeneous part of our solution for x, is going to look like the following. It's going to be c1 times e to the version of this. Remember, this is a positive number, so the square root, the whole thing is giving us a real number up here, but it's going to be to the negative lambda plus the square root of lambda squared minus omega squared times t. And the second linearly independent part of the solution will be e to the negative lambda minus that square root term, lambda squared minus omega squared t. But these are both, in this case, real numbers. So I should say they're distinct real numbers. So they're both real, and they're definitely going to be distinct values. So yeah, let's do it like this. That's a better way to do it. So these are distinct real values. And furthermore, because we know that basically both of these terms had to be positive, right? Obviously, omega squared has to be positive because it's squared. We already said lambda itself has to be positive because lambda came from beta over m, or at least it's half of that or whatever. And so beta was positive, m was positive, so lambda itself is also positive. So in this case, because lambda and the omega squared are both greater than 0, we also know that both of these exponents are going to be negative. So let's see that in action. So basically, we know that the negative lambda term is obviously negative, so this part that appears in both. So we're starting with a negative lambda, and we are, in this case, subtracting some positive value from that. So that one's definitely going to stay negative. It's a negative number, and we're subtracting some other positive result from that, so this is definitely going to stay negative. But what about this one? It's a negative number, but we're adding some positive value to it. So this is obviously negative. And we know that this term, the lambda squared minus omega squared, is less than lambda. How do I know this? Well, we are basically taking a term that's positive, lambda squared is positive, and we are subtracting some omega squared from it. So basically this term, lambda squared minus omega squared, is necessarily going to be less than lambda squared, and then we're square rooting it. So if this term inside the square root is less than lambda squared, then the whole square root of that will be less than lambda. And so I know that this term is less than lambda. So even though in this case I'm adding this whole term in, I'm adding in a term that's less than lambda. I have negative lambda plus some term that's less than lambda. So that means negative lambda plus that term is still going to be less than 0. It'll still stay negative because this piece that I'm adding back to the negative number is less than the negative number itself. Okay, so that's case 1. We are going to get, in this case, notice our results are exponentials, and the powers, both exponents, are going to be negative real numbers. That is our overdamped case. No oscillations. These are pure exponentials for our solutions. Let's look at case number 2. So case number 2 is, what if things work out so that the values that are picked for the coefficients up in our initial problem are such that our lambda squared minus omega squared is equal to 0. So in this case, let's say that the lambda squared minus omega squared term is equal to 0 instead of being greater than 0. This is what we call the critically damped case. And what's happening here? In this case, the solution is, we'll recall, if that term is 0, it gives us the following. So this gives solutions of the form our x homogeneous is going to be equal to C1 times e to the negative lambda t. And that's because, again, I'm basically plugging into this same form that we have here, but now we said that lambda squared minus omega squared is equal to 0, so this whole term is gone. But that means that we also have a repeated root. So it's a real number, and it's negative, but it's a repeated root. So what did we have to do for our solutions when we had repeated roots? Well, the first one is always just C1 times e to the negative lambda t, whatever that root is. And the second one picks up an extra factor of t. And so there's what the solution looks like in this case. And so notice that t is growing, but it grows at a linear rate, whereas this term is an exponential and it's decaying because the power is negative. So even though this term is trying to grow, as t goes to infinity, this term is going to go to infinity, this term is going to 0. And it turns out that this term goes to 0 much, much faster than this term goes to infinity. And so even though we have this term that looks like it's trying to grow, the whole thing is still going to go to 0. So even though t grows, this term, the exponential, decays faster. And so the whole solution will ultimately look similar to the overdamped case in the sense that we won't see any oscillations. We may see something where we eventually basically just, it's all going to go to that 0. So the solutions don't oscillate and look similar to the overdamped case. It's kind of hard to tell visually between an overdamped and critically damped case. That is not the case with our third case. So case number 3. And this is the case where I want my lambda squared minus omega squared to be less than 0. This is our underdamped case. And in the underdamped case, we get solutions that look like the following. Okay, so this is going to have solutions that look like x homogeneous is equal to C1 times e to the negative lambda t, because in this case, again, coming back up to the equation here, we're essentially always plugging into this equation, but then just doing what we can to simplify. We're going to get e to the negative lambda t times e to this square root times t. So this is the e to the negative lambda t, but this square root now has a negative term inside the square root, which means when we take the square root of the negative, it's going to become imaginary. And when we have e to imaginary powers, those always turn into sines and cosines. So this will give us c1 e to the negative lambda t times a cosine of the square root of, let me get this correct here. Let me make sure I don't screw this up. This is now negative, so I need the version to be positive. So omega squared minus lambda squared. There we go, times t. And the second part, as you'll recall, looks like the same thing, but with a sine function instead of, again, omega squared minus lambda squared times our t. So in this case, we have decaying exponentials sitting in front of sines and cosines. The sines and cosines are going to be things that are oscillating, and the decaying exponentials will cause the amplitudes, in a sense, of our sines and cosines to eventually go to 0. In the absolute last case, and it's really a subcase of this underdamped case, what if there had been no damping at all to begin with? Right? So basically, if the undamped case, if beta was 0, if we didn't have any damping, back in our picture up here, without any damping, we expected to just see oscillations that continued forever. In terms of a solution, I would expect that to be basically sines and cosines without any of these exponentials causing the amplitude to decay. And would we get that if we look at this? So we're saying it's the same equation, but now this middle term is gone because this is the friction term, so no more friction. If this middle term is gone, that means that this middle term is gone, and it means that our lambda term is equal to 0. And so coming back down here, if lambda is equal to 0, then obviously this thing's going to be negative here. But if lambda is equal to 0, what happens to our exponentials? Well, if lambda is 0, this exponential just becomes a factor of 1. And same thing here. We just get a factor of 1. And even simpler, we wind up with just getting cosine of, again, because this lambda term is gone, the square root of omega squared. Well, if I'm taking the square root of something that's been squared, I would wind up with just cosine of omega t plus sine of omega t. And the C1 and C2 would still be there as sort of the factors in front. So in this case, note, if there's no damping, then lambda equals 0, and we get, in that particular case, our x homogeneous would look like this: C1 times cosine of omega t plus C2 times sine of omega t. These exponentials, again, become just factors of 1, and this square root term just simplifies to be the square root of omega squared, which just simplifies to omega by itself. Okay, so that is a subcase of this particular case. If there is no damping whatsoever, there's no exponentials, we just get pure sines and cosines that continue indefinitely. Okay, so I want to think about a couple of other ideas and then maybe do 1 or 2 examples to get you through this homework. But there's one other important idea that I want to talk about before we jump into that stuff. And so let me try to give the condensed version of this before this video gets too much longer. So as a side note, a side note within a side note within a side note, it seems like. What I want to think about now is, what if we return to the idea of forcing? All of these solutions here were our homogeneous solutions, right? They assume that basically the f of t term is not present. So what happens when we do indeed have some f of t term? What happens when we get harmonic forcing? So not just any forcing, but harmonic forcing. When I say this word harmonic, harmonic just means, if you aren't familiar with it, just means basically oscillating, sines and cosines. So let me just put that in parentheses here. Harmonic equals oscillations, specifically sines and cosines. Okay, so we've got this system, this mass spring system, that naturally oscillates. And it has some sort of natural frequency that it would normally oscillate at. That frequency is essentially this term omega that we've got here. So it's going to oscillate in some natural way. Let's say that we apply an additional forcing term. Come on, zoom in here. Okay. So let's let our forcing term, f of t, look something like, maybe it's some a times cosine of omega naught t. So we apply some cosine term. Or more generally, and this will make it easier to work with, instead of specifically picking the cosine function that we've done here, I could have just as easily picked sine function. Or more generally, let's call it the following. Let's call it a times e to the I omega naught t. Right? And we know that whenever we have e to an imaginary power, it's going to yield some combination of sines and cosines. In this case, ones that involve a frequency in our forcing of this omega sub 0. So this omega sub 0 is the frequency that we are basically forcing this thing at. So we're adding energy to it in some manner. So let's just think about physically what I'm talking about here. We have a mass spring system. Forget about the forcing for now. If we have our mass spring system and we pull on this mass and let it go, it's going to oscillate. And it's going to oscillate with some natural frequency. That frequency is dependent on all of these input factors that go into the result. So obviously that natural frequency is basically related to this omega term. But omega, if we come back to the original equation, this omega term is going to be related to both k, the spring constant, and then also m, the mass. So basically it makes some sense, right? If you have a really stiff spring, that would affect the spring constant. That's going to affect how fast this mass vibrates or oscillates on the spring. A second thing that will affect how fast it oscillates is how heavy that mass is. Right? If the mass is really quite heavy, you would expect that that will slow down the oscillations. If the mass is really light, the oscillations could happen much more rapidly. So basically, m and k, the mass and the spring constant, are what ultimately determine the rate of oscillation, this omega term that shows up. Okay. Now let's come back to forcing. So our system naturally oscillates essentially at some frequency omega. That's how quickly it oscillates. We're going to now add an external forcing. So we're applying a force to the mass from the outside, magnetically, who knows how, we're pulling on it with some other thing is applying forces. And it's also applying a force that is oscillatory in nature. But it's at a different frequency. It's at omega naught, omega with the subscript of 0 instead of the omega that we had up here. So this W up here is, or this omega up here is different than this omega down here. But we're applying some forcing. What happens if we were going to try to actually find our full solution? So in this case, our forcing term is purely sines and cosines. We know that, so the forcing is pure sines and cosines, while the homogeneous solution, x sub h, involves, depending on the situation that we saw above, right, it can take any one of these forms. It could look like this, it could look like this, it could look like this, or it could look like this, depending on, again, the values of lambda and omega. So depending on all of those values, it involves other terms, potentially some sort of negative exponentials. If we have damping, there's some negative exponentials involved. Involves negative exponentials. Assuming there's some damping. So any damping will lead to something involving negative exponentials. What this means is when we try to find our particular solution based on the forcing term, we don't need to worry about the situation where our forcing term looks exactly the same as the homogeneous solution, and we have to start getting clever about adding extra factors of t and so on and so forth. Not yet, at least. So we can find our particular solution using the method of undetermined coefficients. So using the method of undetermined coefficients, we want to find the particular solution, which we'll call x particular. So what we would probably guess, based on what we know from doing that, is basically if the form of our forcing term looks like a pure sine and cosine, or in this case, if it looks something like this, then the guess for the particular solution should also be something that looks similar to that. So I'll call it, instead of using A, I'll use some letter C instead, but it's going to look like e to the I omega naught t. That would be our best guess. And I don't need an extra factor of t here because we're essentially safely assuming that the form of our particular solution will not conflict with the form of the homogeneous solution, because we know the homogeneous solution has these negative real exponential terms, whereas this term, because of the I here, really is just pure sines and cosines. And so using our method of undetermined coefficients means I also need to find x p prime and double prime. So basically take the derivative and second derivative of this. When I take the first derivative, I will get c. I will pick up a factor of I times omega naught, and I will have ei omega naught t. And then when we take the second derivative, again, I'll have my c there. I'll pick up another factor of I omega naught. So I'll have I omega naught squared times ei omega naught t. And this term here is going to involve an I squared and omega naught squared. But what happens when we square I? Well, I is, by definition, the square root of -1. So when we square it, it gives us a negative sign. And we're going to get negative c omega naught squared e to the I omega naught t. And we plug in. So plug into the ODE in order to try to solve for this coefficient c. And we will get, where's that differential equation? Way back here. So we're plugging it all the way back into this differential equation right here at this line. So this is what I'm plugging in the particular solution into in order to try to solve for that coefficient. So let's come back down and do that. So the first term just looks like it's going to be the xp double prime, so it's going to be negative c omega naught squared e to the I omega naught t. If I can write a little more clearly here, let me try to zoom in and get my writing to be a little clearer. Okay, negative c omega naught squared e to the I omega naught t. So there's the xp double prime term. From there we had plus 2 lambda times the first derivative term, so times c I omega naught e to the I omega naught t. And then the last term was plus omega squared times the function itself, so c e I omega naught t. And that whole thing is supposed to be equal to our forcing term, which is this form right here. So that's equal to a times e to the I omega naught t. Every single term has the I omega naught t term in it, so we can cancel all of those, basically divide out by this term all the way through. And we wind up with the following. We wind up with negative c omega naught squared plus 2 lambda c I omega naught plus omega squared equals a. And if we try to solve for c, oops, and I missed a factor of c on that last term, so let me sneak that in. If I factor the c out and divide both sides by the remaining term, what I'll get is that c is equal to a over negative omega naught squared plus the 2 lambda I omega naught plus omega squared. Whew. So this big ugly mess here. Okay. If we rearrange things a little bit, I'm going to just group the omega squared term and the omega naught squared term together just to make life a little bit easier. So omega squared minus omega naught squared plus the 2 lambda I omega naught. Okay. So with all of this said and done, our particular solution is the following. we are going to get that our particular solution, x particular, is equal to c e to the I omega naught t, where this is the c that we've just found. So you could think of it as the following. I'm going to factor out some stuff here, and we'll kind of write this in an ugly way here, but let's just do this all as written for now. Oops, missed my lambda. So there's the coefficient times e to the I omega naught t. And oftentimes you'll see this written as the following. Basically, they will factor an a out and call the rest of this function, this g function, where g of this I omega naught determines, in a sense, the amplitude of our oscillations here, right? We have this term that represents oscillations. The a is can be wrapped up in that, and this term here is going to kind of scale those oscillations up and down. So this g of I omega naught term looks like this: omega squared minus omega naught squared plus 2 lambda I omega naught. Okay. The whole point of factoring this out is just to say that this g term plays a role in determining the amplitude of the oscillations. So again, this looks kind of scary because you're not used to seeing sine and cosine functions written like this e to the I omega naught t, but again, in reality, whenever you have e to an imaginary power, this term is really just a bunch of sines and cosines. And whatever's sitting in front of those sines and cosines is the amplitude. And so in this case, obviously the a plays a role in the amplitude. That's the amplitude essentially of the forcing being applied, right? A was how big are the oscillations being applied in terms of the force. And the remaining part that determines the amplitude of these oscillations is this g I omega naught. And so I want to think about what happens in a couple of cases. What happens, for example, if there's little to no damping? So what happens if there is little, or even better, no damping? So little or no damping, meaning that lambda is basically 0. And what if the frequency that the applied oscillations, remember the applied oscillations are occurring with a frequency of omega naught, the natural oscillations of our system occur at a frequency of omega. What happens if those get close? The forcing frequency matches the natural frequency so the forcing frequency matches the natural frequency of the mass spring system. So what I'm suggesting is that our omega is approximately the same as omega naught, that these two values, my handwriting is getting extra sloppy here, let's try to clean that up a little bit, but that omega is approximately the same as omega naught. So what happens in those two cases? Well, looking at this function, if lambda is approximately 0, this term is gone. And if omega and omega naught are essentially the same, then this denominator, if this term is basically gone to 0, And if these two terms are the same and we're looking at their difference, that difference is going to 0. The whole denominator is approaching 0. And if the denominator is approaching 0, what's happening to the overall function? It's getting incredibly large. In this case, our g of I omega naught approaches infinity. It gets very large. It's our amplitude. Large amplitudes. There's a natural phenomenon that corresponds to what we're seeing here. This is the phenomenon of resonance. And so if we actually go back to the equation way up here, here's kind of the case we're talking about. What I'm suggesting is if there's no damping, which was one of the assumptions we made, our solutions look like this, pure sines and cosines. If the forcing term also looks like a pure sine or a pure cosine, and the omega naught of the forcing term matches the omega of the natural frequency of the system, so that these two are the same, well, now my particular solution will match exactly with part of the homogeneous solution. And how do we change our guess for our particular solution to account for that? We have to add an extra factor of t to our particular solution. And that extra factor of t is what leads to a growing oscillation in our particular solution, which corresponds exactly to the idea of resonance. Resonance is where the forcing frequency matches the natural frequency, and it induces incredibly large vibrations. When you see the opera singer in a cartoon singing and hitting a note and all the wine glasses bursting, the idea is that the frequency of the forcing term, her voice, the air pressure waves caused by her voice, exactly matches the natural vibrational frequency of the glass in the wine glass. And when those frequencies match, the forcing term grows basically without bounds. The particular solution grows without bounds. The amplitude of those grow without bounds. And eventually the molecules will vibrate so much in the wine glass that it will shatter itself. That's the idea. Same type of thing if you've ever been driving in a car on the highway and you crack the window, just one window, the wrong amount. There's some natural frequency of sort of the vibrational frequency of the air in your car compartment. When you open the window and the air starts flooding in the right way, if the forcing frequency of how that air is entering the car matches the natural frequency based on the shape of the air within the car, and you start to get that whoa, 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 whoa sound, that is the same thing. The vibrations are basically syncing together, growing in amplitude to the point that those pressure vibrations hit your ears and you can actually hear the incredibly large sort of vibration. That's the idea of resonance. Okay, so conceptually, this is a huge topic, and we're going to be spending a lot of time on this, but we really haven't touched on how to do homework problems from this section. So let me give you a quick couple examples to get you started on the homework as well. Whoa. So let's look at an example. An example from the homework here, or one similar to one that will be on the homework. I will mention also before I jump into this problem, there are a couple other examples in the book. They do an analogous series and circuit approach. So basically like in electronics, you can do a series circuit that can be modeled using these same type of differential equations. Essentially, the idea of electrical resistance plays the role of damping, and the conductivity and various things like that play the role of spring constants, all of that. And what you get is basically an analogous system. Looks exactly like the mass spring system, but instead of oscillations in the position of a mass, you get actual oscillations in the electrical current that's flowing through it. I'm not going to do that, but you might want to read that section if you're planning on being an electrical engineer. It's kind of a cool topic to take a look at. So let me just mention that now. That exists, even though I'm not going to actually do one of those specifically here. Okay, so let's try this one. Let's say that we have a mass weighing 20 pounds. And let's say that this mass stretches a spring 6 inches. Okay, so the equilibrium position of the spring is basically 6 inches stretched from the natural length of the spring when this 20-pound weight is applied to it. If this mass is then released, so if this mass is stretched an additional 6 inches and released, we want to give basically the differential equation, modeling this, and then potentially solve it. Give the position of the mass as a function of time. And let's, for this one, assume there is no damping. Okay, so in this one, we're assuming no damping. So basically, we've got our spring, it's hanging down, and the mass is now 20 pounds, and it stretches it a distance of what we were calling S before, of 6 inches. So in this case, to find, we have a differential equation that looks like this. So let's start with this. We know our differential equation looks like this. It looks like m d squared x dt squared plus beta times dx dt plus k times x. And in this case, there's no external force being applied, so it's equal to 0, no external force being applied. We also said that there's no damping, so this term is 0, meaning this whole middle term is gone. The mass isn't given. Instead, the weight is given, and this is a very confusing thing for people that are kind of new to these types of problems. When we talk about a mass weighing 20 pounds, 20 pounds or pounds themselves are not actually typically a measurement of weight or a measurement of mass. They're a measurement of weight, and the distinction is that weight is given as a force. So this is a measurement of force. The corresponding imperial units that correspond to mass are actually called slugs. And it's confusing because often in plain English, we interchange the word pounds. There's the idea of something called basically mass pounds and force pounds. And normally what we think of is a force, but on the surface of Earth, where gravitational constant is basically uniform, right, we don't really need to distinguish between those two different things. But I want you to just know that when we talk about pounds in physics classes, or in this class, this is not a mass, this is a force. So let me write that here. Note, pounds, is a force, not a mass. So we need to figure out the corresponding mass, and we also need to figure out the spring constant that's going to get this thing to all work out. Okay, so if I can get this all on the page here. I want to go back way to the beginning of our lecture. Way up here. And I want to talk about basically this situation right either here, or maybe a better spot to look at it is right here. We want to look at our system in its equilibrium position, where there's only two opposing forces, the force of gravity pulling down on it, and then the force of the spring pulling back up on it. And I'm going to use those to find our mass and our, oh, come on now. So there's two forces. So I want to find our mass and our spring constant. I know that when this is at equilibrium, what we're calling Ks equals mg. And right now, mg is 20 pounds. This whole thing is already 20 pounds. On this side, we have k times s. K is the spring constant, and s is the length, the distance that our mass, or that our spring, has been stretched due to the mass. In this case, it's 6 inches. So we can do this in units of inches if we like, and we could use s equals 6. Or we could do this in units of feet, and we could use s equals a half. We just have to pick units. So in this case, I'm going to use whatever. Let's stick to inches. So we have 6 inches. And again, just keep that in mind. That's inches. So what are our units for K? What do we get for K? So the force of gravity was 20 pounds pulling down. Our force of our spring was K times S, where S, the length that had been stretched, was 6 inches. If I divide both sides by 6 inches, we're going to get 20 over 6 with units of pounds per inch. And we can simplify 20 over 6 down to 10/3, or write it as, a decimal if we'd like, 3 and, what is that? 3 1/3. So whatever, 3.3 repeating pounds per inch is our spring constant in this particular case, assuming I didn't totally butcher that. Okay, so that is the spring constant. What is the mass? Well, the mass is part of the term that goes into this. So the second term, so this is where we found K. So let's do that separately. So over here, we found K. Now over here, I want to find M. And again, M is going to be given in the units of mass in imperial units is slugs. And so I'm going to call this mg, which we already know is equal to 20 pounds, but we also know the gravitational constant acceleration g. So in this case, we know that mg equals 20, but g we will approximate as 32 feet per second squared. And I think that's the value that they'll use in the book. I think they just rounded the nearest. It's closer to like 32.2. Let me just check and see. What do they use? Yeah, they use 32 feet per second squared as opposed to a higher, more accurate number. So to solve for m, same thing. M is just going to be 20 divided by g, which is 20 divided by the 32 feet per second squared. And the 20, again, had units of pounds. So we have pounds divided by 32 feet per second squared, and you can get the coefficient for whatever this winds up being, which again, I don't have a calculator on me right now, so I'm not going to be able to do this one in my head, but whatever decimal you get out of that. So our equation, so putting these together, our ODE is the following. So again, we already wrote it up here. It's the mass times dx dt, or the second derivative of x with respect to time, plus k times x equals 0. And now we've found our mass right over here, and we found our spring constant k right here, or right here. So putting these together, our mass, I'll just write it as, I guess I can at least divide both of those by 4, so that's what, 5/8. All right, so this simplifies to 5/8. And that has units of slugs. Pounds divided by foot over second squared gives you slugs. So we have 5/8 times d squared x dt squared. That's our coefficient for m. Plus, what was k? K was 20/6, which I could write as 10/3, or we could write it as the 3.3 repeating, but that was times x equals 0. And this is our differential equation. The initial conditions, in this case, based on what was said, is we were to stretch it another 6 inches and let it go. So sorry, x at time 0. So x at time 0, come on here. X at time 0 is equal to 6. We stretched it 6 extra inches and let it go. And when we say we let it go, the idea is that we let it go with an initial velocity of 0. So there was no initial velocity given to the object. We just stretched it, stopped our hand, and let go of it. And so the initial velocity is 0. The initial displacement is 6 additional inches. And this is the differential equation that we could then solve in order to find the position of the mass as a function of time. So solve to find x of t. And in the interest of time, I think I'll skip doing that. If people have questions, we did a bunch of these in the homeworks for chapter 4, so it's the same thing we were doing in chapter 4. But these are the types of problems that you are going to see. Let's do one more of these. Let me pick another problem here. Let me make one up. Okay, here's a decent one. A 1 kilogram mass is attached to a spring whose spring constant, is 16 newtons per meter. Oops, the entire system write entire system is submerged in a liquid or a fluid that imparts a damping force that is numerically equal, at least to 10 times. So, and when I say, again, I should say numerically equal. That is an important word to sneak in there, because the units don't match, but numerically equal to 10 times the instantaneous velocity. Determine, again, the equation of motion And for us, we'll just determine the ODE, but in the homework, you'll have to actually solve the ODE as well for some extra practice. But determine the equation of motion if, let's see, the mass is released from a position 1 meter below equilibrium position with an upward velocity of 8 meters per second. Whew. Okay, so here is our big mess of a problem. Again, our goal is to set up the differential equation with the appropriate initial conditions, and then ultimately solve that differential equation, assuming we have time to get through it all. Okay, so our equation looks like this. md squared x dt squared plus beta dx dt plus k times x equals 0. There's no forcing term on this particular one. And we need to specify basically x at time 0 equals something, and x prime at time 0 equals something. So this is what we're trying to come up with. The mass is given in this case. When it's given in kilograms, kilograms are a measurement of mass, unlike pounds. So that I can directly go and plug that in for our mass here. So to find m, we know m equals 1 kilogram. If we're trying to find beta, that is our damping coefficient here. And we know that where it talks about the damping, it says the whole system submerged in a fluid that imparts a damping force numerically equal to 10 times the instantaneous velocity. So what it's telling me is that this term, which is the damping force, so beta dx dt should be equal to 10 times the current velocity. But the velocity is dx dt. So basically I can cancel that on both sides, and we find out that beta is equal to 10. What are the units, incidentally, of beta? We know that mass was equal to 1 kilogram. We know that the units of all these terms have to be force, right? I can't add up different quantities that have different units. So that means this has to have units of force. So what are the units of this? Well, if we remember that force is equal to newtons, which is kilograms times meters per second squared. And in this case, the way it's set up, beta is multiplying dx dt. So we have beta times something that's multiplying, or times a velocity, so times meters per second. What do the units of beta have to be? Well, we have to include the kilograms, and we're missing a seconds in the denominator. So this has units of kilograms per second. Those are my units of my damping coefficient. So 10 kilograms per second. And the last one, K, our spring constant. They already gave us the appropriate number for that. They said it was 16 newtons per meter, which is exactly the units that we would want. Kilograms times meters per second squared, another name for that is newtons. In this case, again, this term needs to be have units of force. We know that K is our spring constant, and X already has units of length. So if X has units of length, we've already taken care of this. So in this case, our Kx, our K is equal to 16 newtons per meter. But another way to think of newtons per meter based on all of this is kilograms times meters per second squared, and then that's newtons. So this is newtons, and then we're dividing it by meters. And the dividing by meters would give us kilograms per second squared as another way of giving the units of our spring constant. So we get, out of all of this, m was equal to 1, so we just have d squared x dt squared plus 10 dx dt plus 16x equals 0. There's our equation. And in this case, we need to find and plug in our initial conditions. So the initial conditions say that, for one thing, the mass is released 1 meter below its equilibrium position. So if we've got our setup like this, right, here's our mass hanging down here, and maybe this is the equilibrium. Assuming that we have decided that this downward direction is our positive direction, which needs to be in order for the signs of everything here to match up the way that they were supposed to. So assuming that this is our positive direction, the mass being 1 meter below means that it's gone 1 meter in the positive direction. So that's 1 meter. Here's 0, here's 1 meter. That tells us that the initial position of this, x at time 0, is equal to positive 1 meter, because in this case, below is in the positive direction. It's downward. But the initial velocity is 8 meters per second upward. If the velocity is 8 meters per second upward, well, relative to the direction of our axis here, upward is the negative direction. So that tells me that x prime of 0, our initial velocity, isn't 8. It's instead negative 8. So our initial velocity is 8 meters per second in the negative direction, which is upward. So just remember, down equals positive in this case, and up equals negative according to our drawing. And so this is the differential equation with the appropriate initial conditions. We would solve this relatively straightforward using our, let's just do this one. So to solve, get our characteristic equation. Our characteristic equation for this is going to be, again, I'll use m because that's largely what the book uses, but you're welcome to use r or some other letter if you prefer. But we get m squared plus 10m plus 16 equals 0. We need to solve for m in this case. I don't see a real obvious way to factor this, so I think we're just going to use the quadratic formula. M should be equal to negative 10 plus or minus the square root of 10 squared, which is 100, minus 4ac, so 4 times 1 times 16, all over 2a. So we get from this negative 10. This term is going to be a 10 minus a 64, which gives me 36. So we got, let's see here, plus or minus the square root of 100. Oops, I already did that in my head. 100 minus 64. So 100, this term is 64, gives me 36. Come on now. 36. And then we're dividing the whole thing by 2. And so I'm going to get negative 10 plus or minus 6 over 2. If we do the negative 10 plus the 6, I'll get negative 4 over 2. And for the other term, I'll get negative 16 over 2. So m is equal to either negative 2 or negative 8. And I guess I was just a dummy that couldn't factor that in my head. But there the two answers are. And so that tells me the position, in this case, it's going to be one of our overdamped cases, no oscillations. The position is going to be x of t equals c1 e to the negative 2t plus c2 e to the negative 8t. And now we need to plug in our initial conditions in order to find C1 and C2. Right, there's no particular solution because it was homogeneous, so we don't need to worry about that. But we know that x of 0 equals 1. So when I plug in x of 0, whoa. When I plug in x of 0, so plug in t equals 0, we're going to get C1 plus C2. That's supposed to be equal to 1. I just got these because both of these powers, when the power becomes a 0, are just 1s. And then the second one says that x prime of 0 is equal to, what did I pick? -8. Just made up these numbers, so let's see. If this is x of t, then x prime of t is going to be -2c1 e to the -2t minus 8c2 e to the -2t. And so when I plug in 0 here, I'm going to get -2c1 minus 8c2, and that's supposed to be -8. Okay, so let's see what we get out of this. I can do either a substitution or an elimination method. I'm going to do an elimination method in this case. I'm just going to double the top equation. And I'm going to add the two equations together. And I will get 0 for the c's. So basically, I'm just adding them together. I'll get -6c2 equals -6. And that tells me that c2 equals 1, assuming I didn't screw that up. And if c2 is equal to 1, then that tells me that, going back to either one of the equations, we can plug this into either of the equations here or here. So let's go to the top one. If C2 equals 1, then that tells me that I've got C1 plus 1 equals 1, which was the original equation that we had before I doubled this top equation. So C1 plus C2 was supposed to be equal to 1. And what does that mean that C1 has to be equal to? Oh, come on now. C1 must be equal to 0. So we get, in this case, we get, for our solution, that x of t is equal to simply -6 e to the -8t. Hopefully I didn't totally screw up some algebra in here. But that looks, I don't see any obvious mistakes here at least. So hopefully that's right. Cool, so there's our solution. That's how you would solve one of these equations. But really the most important thing is going to be, can you translate the word problem into a setup that's correct, like this? So getting the setup correct is going to be more important on these problems than ultimately solving them. We're going to get plenty of practice doing both.